Hello everyone and welcome to the Maths Live channel of Sonone sir. Friends, up to this point we have discussed so many topics and what we have started in the last session is series solution of linear differential equation with variable coefficients, and in that up to the ordinary point we have completed. So today we are going to start little bit a difficult concept as compared to the ordinary point, that is series solution about singular point. So singular point concept we are going to start. Output of today's video is find the series solution of linear differential equation at singular point. So at the end of this session you are able to solve linear differential equation with variable coefficient at both the points, that is ordinary point as well as singular point. The method used for solving such a type of linear differential equation is called Frobinious method. So today we are going to start Frobinious method, and let's hope we will understand completely the concept or the procedure to solve the problem based on Frobinious method. So let us start the actual concept. Let us consider our linear differential equation of order 2 with variable coefficient. Here p0 of x d2y by dx square plus p1 of x dy by dx plus p2 of x y is equal to 0. This is our second order linear differential equation. Here p0, p1, p2 all are functions of x. We have solved such a type of problems in while finding the solution with ordinary points. Now let us first define singular point, and then I will explain the Frobenius method. Now here singular point means what? P0 of 0 is equal to 0, means in this p0 of x, if I put x equal to 0 and I get 0, then x equal to 0 is called singular point. Understood the concept of singular point? Now singular point has two natures. First one is a regular singular point and second one is irregular singular point. So just define first regular singular point. Regular singular point. A point x equal to 0, is called regular singular point if it satisfies this condition. Limit x tends to 0, because I am taking x equal to 0, so limit x tends to 0, x into p1 of x divided by p0 of x, p1 of x upon p0 of x is finite. If this is there, then we can say that first condition is satisfied. Now second condition is limit x tends to 0, x square p2 of x upon p0 of x is finite. So if these two conditions are satisfied, then we can say that our point x equal to 0 is singular point, regular singular point. And if it is not, then it is called irregular singular point. Irregular if this is not satisfied, otherwise it is called regular singular point. Now we are going to study the solution at regular singular point. So you may call it as a singular point or regular singular point, doesn't matter. Okay. Now how to solve it? Now what is exactly Frobenius method? Frobenius method means finding the solution at a singular point. If I write this equation in this way, d2y by dx square plus p1 of x upon, you may say p0 of x, I can take the value, say x dy by dx plus p2 of x upon x square y is equal to 0. See, I just take p0 of x, value of p1 of x and whatever it may be multiplied by x, like that. I take here x square and I divide by such a type of equation, or you may call it, or we take this one, p0 of x d square y by dx square plus p1 of x dy by dx plus p2 of x y is equal to 0. But Frobinious method gives the solution of this equation. This is our equation. We use the same method to solve it, but Frobinious method is for this equation. That is your Frobinious theorem or Frobinious method. Solution of this equation gives is called Frobinious method. Method of solving this equation, right? So what is that exactly? We take y is equal to summation ak x raised to r plus k equal to 0 to infinity. This is the solution. Y is equal to k equal to 0 to infinity ak x raised to r plus k, right? Or you may write x raised to r summation k equal to 0 to infinity ak x raised to k. So this y is our answer. We have to find values of a0, a1, a2, everything. Now dy by dx is equal to summation k is equal to 0 to infinity. See the difference here. In your ordinary point, here k starts from 1 to infinity, but in singular point your k starts from 0 to infinity, and I get here r plus k ak x raised to r plus k minus 1. Then d square y by dx square is equal to summation k equal to 0 to infinity r plus k minus 1 ak x raised to r plus k minus 2. Okay, so this is our solution method. Now we will see what is the procedure to solve solution at singular point. So let us see the procedure here. Step first is check that the point is regular singular point. Means check that two condition. X into p1 of x upon p0 x square into p1 of x upon p0 of x, limit x tends to 0. If the limits are finite, then we can say that it is a regular singular point. And next one is step second. Take that solution, y is equal to summation k equal to 0 to infinity ak x raised to r plus k. Then its two derivatives dy by dx and d square y by dx square as we discussed, and put these values in the given equation. That is our step second. Understood? Then step third, very important one. Step third decides the answer. So our step third is, I am just reading it carefully and then we understand. Equate to 0 the coefficient of lowest power of x. Equate to 0 the coefficient of lowest power of x. We get one equation in R, and that equation is called indicial equation. That equation is called indicial equation. So which equation we call indicial equation? When we equate lowest power of x equal to 0. Now if I see in these three terms, I can say that x raised to r is the smallest term. But in actually calculation, most of the time it is x raised to r, but sometimes it may differ, and we have to equate that lowest power, coefficient of lowest power of x equal to 0, and we get indicial equation. We will clear this concept in examples, right? And then fourth step. Now what is the, why this indicial equations is very important? Because indicial equations gives us the solution. So what is the solution? Suppose my equation is of degree 2, then I take two roots. R is equal to say m1 and R is equal to m2. These are the two roots, right, of this indicial equation. Now if these two roots are equal, there is different solution. If these two roots are distinct, there is different solution. If these two roots are multiples to each other, different solution. So there are three cases here. So that is our step fourth, you may call it, or case first. Case first is these two roots m1 and m2 are distinct. Roots are distinct. Roots are distinct and not differ by integer. Not differ by integer. Means what? Not multiple to each other. They are totally distinct roots. Then our y is c1 y at m1 plus c2 y at m2. Just at 2 points find solution and add these two, you will get the final answer. Okay. Then case second. Case second is if m1 equal to m2. m1 equal to m2, that is roots are equal. What's happen if roots are equal? If roots are equal, then y is equal to c1 y at m1. m1 equal to m2, so you may take m1 or m2, doesn't matter, plus c2. Then you have to take derivative, dou y by dou r at m2. Sorry, m1, because m1 equal to m2. Means derivative comes into the picture here. Then the third one, case third. If I take a case third here, that is m1 and m2, two real roots, and they are differ by an integer, means multiple to each other. Multiple to each other. What is the meaning of this? Differ by not, it is differ by integer, means suppose m1 is equal to 2 and m2 is equal to minus 2, like that. Or you may take this is minus 2 and this is plus 2, or this is 2 and 4, like that. So when such a case arises, then also we have to use the solution. Our solution is y is equal to c1 y at, you may take say here m2 plus c2 y plus dou y by dou r, y plus dou y by dou r at m1. Here I take m1 is less than m2, right? That's why I wrote in this way. If m2 is less than m1, then I have to change this m1 and m2, like that. Here I required y and dou y by dou r, this derivative, and m2 one solution is there, and m1 y dou y by dou r. So this is the case. Now question still remains, what is my y? How I find this y? To find this y, we need constant. Which are the constants we need? a0, a1, a2 and so on. How we are going to find that? That is our last step. Step, you may say fourth. To find constants, equate remaining powers of or more powers of, remaining powers of or more powers of x, coefficient of, remaining, equate coefficient of remaining powers of x equal to 0. Means we have taken lowest degree, then increase degree by 1, then increase degree by 2, increase degree by 3, like that. Find other values, then you will get y, and from that indicial equation you will get two roots. Put that root, according to root, finalize the solution. So this is the basic idea. Now example based on this we will continue in our next video. Thanks for watching.